All right, today we're diving into a topic that feels like it's straight out of science fiction, but it's quickly becoming science fact. We're talking about quantum computers. So let's break down what they are, how they work, and, why you should even care.
So let's just start with one single, kind of mind-bending question. Our entire digital world, everything on your phone, your laptop, it's all built on bits that are either a 0 or a 1. That's it. Simple. But what if a computer could work with something that's both at the exact same time? That one idea is the key to everything we're about to cover.
And here's how we're going to do it. First, we'll look at the basic building block. Then we'll see why it's so different from today's computers. We'll walk through the 5 steps of how these things actually run a calculation. Then, the fun part, the world-changing problems they could solve. And we'll wrap up with a little reality check on where we are right now.
Okay, Section 1, Beyond Heads or Tails. Look, to get any of this, you have to start with the single most important piece of the puzzle, the quantum version of a computer bit.
Think about it this way. A classical bit, the one in your phone right now, is like a coin that's already landed on a table. It's either heads, let's call that a 0, or it's tails, a 1. It's decided. A quantum bit, or a qubit, is more like a coin while it's still spinning in the air. While it's up there, is it heads or tails? Well, no, it's kind of both. It's in a fuzzy mix of every possibility at once.
And that weird spinning mix actually has a name. It's called superposition. And it's this ability to be both a 0 and a 1 at the same time that gives a qubit its incredible power. It gets to explore a huge landscape of possibilities all at once, while a boring old classical bit is just stuck being one thing at a time.
But wait, there's more. It's not just superposition. There are 2 other quantum ideas you gotta know. First, entanglement. Imagine you have 2 of those spinning coins, and they're, well, magically linked. No matter how far apart they get, if you stop one and see its heads, you instantly know something about the other one. It's wild. Then there's interference. This is a super clever way to basically cancel out the wrong answers and boost the signal of the right ones. Seriously, think of it like noise-canceling headphones for a computation.
So with those crazy ideas in mind, let's see what kind of a machine this actually builds. This is where we get into the real difference between a classical and a quantum computer.
All right, let's put them side by side. Your laptop uses bits, 0 or 1. A quantum computer uses qubits, 0 and 1. Now here's the kicker, the power. Add another bit to your computer, and its power goes up a little bit, nice and linear. But add another qubit, the power grows exponentially. That's 2 to the power of n possibilities. But all that power comes at a cost. Qubits are unbelievably fragile. The slightest vibration or change in temperature, what they call noise, can mess everything up. Your classical bits are rock solid. That's why your laptop is perfect for email and games, but these quantum machines are being designed for very specific, mind-bogglingly complex problems.
So how do you actually use one of these super powerful but super fragile things? Well, it's not magic. Turns out it's a very deliberate, structured 5-step process.
Let's walk through it. First, you initialize. You set all your qubits to a known starting point, like setting all your coins to heads. Easy enough. Second, you put them into superposition. This is where you get all those coins spinning, representing every possibility at once. Third, you entangle them, creating those spooky, powerful links between them. Fourth, you apply what are called quantum gates. This is the actual program, and it's designed to guide that interference we talked about, canceling out bad paths and amplifying the good ones. And finally, number 5, you measure. You basically look at the qubits, which forces them to stop spinning and collapse into a final answer, a definite 0 or 1.
Okay, that whole process seems incredibly complicated, right? So why on earth are we bothering with all this? That brings us to the really exciting part, the kinds of unsolvable problems that make this all worth it.
The potential here is just staggering. We're talking about things like designing new drugs and materials molecule by molecule with perfect accuracy, or solving optimization problems, like finding the absolute best, most efficient route for every single package a global logistics company sends. We could speed up specific AI tasks and even simulate incredibly complex financial markets. We're talking about tackling problems that would take the best supercomputer we have today literally longer than the age of the universe to solve.
And then there's the big one, the double-edged sword, cryptography. See, that same incredible power that can design new medicines could also be used to break the very encryption that protects almost everything in our digital lives. Your bank account, your private messages, government secrets, all of it. This threat is a massive, massive driver of research in the field.
But, and this is a really big but, we have to keep our feet on the ground. This quote here says it all. We've seen quantum advantage, a real speed up for some very specialized problems. But the idea of broad, everyday advantages for you and me, that's just not here yet. Not even close.
Which brings us perfectly to our final section. Let's do a reality check. What's the road ahead look like? What's actually happening in labs right now?
You know, the progress lately has been really tangible. We've had these huge milestones, like back in 2019 when Google had a machine perform a task that would have been practically impossible for a classical supercomputer. You've got giants like IBM and Google publishing these detailed roadmaps for scaling up their machines, and maybe most importantly, we're seeing huge breakthroughs in error correction, the tech needed to deal with how fragile these qubits are. And the coolest part? You can actually log on to the cloud right now and run code on a small quantum processor yourself. It's becoming accessible. So what all this means is that we're in a new phase. The field is shifting away from just doing proof-of-principle experiments to show this stuff is even possible. Now it's all about the hard engineering work of actually building the foundations for reliable, large-scale machines that can do something useful.
And that leaves us with this final, really fascinating thought to chew on. The first quantum revolution, which was just our basic understanding of how the atomic world works, that gave us the transistor. And the transistor gave us, well, our entire modern digital age. This, right now, is the second quantum revolution, where we're directly harnessing those weird quantum rules for computation. So the real question is, what world-changing thing will this second revolution give us?